A CDMA system used different orthogonal codes to separate the user transmissions from each other, and at the receiver side we use a despreader, which relies on cross-correlation, to despread the signal and to extract the user signal and do the separation from other signals. You know this receiver chain from the different from the last lecture. So here's the spectrum signal, and here's a cross-correlated despreader, and the despread signal can then be fed into the data detector, and what we get is the reconstructed data here. But you need to know the code used for spreading. So you need to generate the same code which the user used to spread its signal. And if you select the right code, then you get a good cross-correlation pattern here. So yeah, here's the maximum for the cross-correlation, and after one code length the next symbol comes, and then you have a maximum again. But for a different orthogonal code which a different user uses, you get almost no correlation. Yeah, so this is the trick behind CDMA to do the multiplexing for users. And to make this work, you need a good code which has good properties so that this correlation pattern can be achieved. So high correlation for the same code and a very weak correlation, low correlation output here for different orthogonal codes. And this is a matter of code design. The code design is a very complex topic, so there are many different codes and there's a lot of mathematics behind this. We won't go much too deep into this too much. There are other lectures on code design and literature, so if you're interested, then please consult the literature about this topic. We just have a look at one code, but we will come back to this later. In the CDMA system, we have different situations. So here we use the direct sequence CDMA system as an example. And the first situation is the synchronous CDMA. So the CDMA relies on spreading codes, and different users use different spreading codes, orthogonal spreading codes. But what matters now is the start of the code on the time axis. And here in the synchronous case, both users are synchronized, and the first code symbol of both codes started at the same time. So okay, so here the same index is used, but actually the two users use different codes here, of course. So both codes are orthogonal, but that is not the not important here. The fact is here that both codes are synchronized and they start at the same time in both users. So the signal which they generate is spread, but the data behind the spread signal is synchronized, and so the code is also synchronized in the time. And Then the opposite case is the asynchronous Cdma case, where the two users are not synchronized, and it's totally random when their transmission starts. So here for the user 1, the transmission and the code starts here at this point, and for user 2 there is some other start of transmission time point here. So it's completely random and it cannot be determined. So here the receiver has some pre-knowledge about the signal which it receives. So at the receiver side, both signals overlap, and a more complex spectrum signal consisting of the two independent spectrum signals is created, but the receiver knows that both transmitters are synchronized. And here the users are not synchronized, and if both signals overlap, then the receiver has no pre-knowledge about when the user started the transmission actually. And these two cases have consequences on the selection of codes, because you can you have to select different codes with different properties for the asynchronous case than for the synchronous case. But now we have a look at the synchronous case and one code which can be used to implement a synchronous Cdma system. So here the central point is that two codes must be orthogonal so that they can be allocated to different users. And the code which we consider here as an example is the Welch code. Of course, there are other codes, but this is one example to show you how the Cdma works in general. So the Welch codes are constructed from Hadamard matrices. They have a special structure. So Hadamard matrix is constructed of other Hadamard matrices with half of the order. Yeah, so here's an example. So the most simple Hadamard matrix is just a 1. And now if you apply this rule and you have a Hadamard matrix of order 2, then just place the 1 here. And the last sample of the H1 matrix is just inverted. And same goes if you double the order again. So here's the Hadamard matrix of order 2, and you will find it here, 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 and the last one is inverted. This is how Hadamard matrices are constructed. And now let's have a look at the rows and columns of the Hadamard matrix. So what you first notice is that the Hadamard matrix is symmetric, and so the first row equals the first column, second row equals the second column, and so on. So it actually doesn't matter if you have a look at the rows or columns. But what's interesting here is that the rows and columns form orthogonal vectors. So if you take the first row out as a vector and then take the second row out as a vector, you see that both vectors are orthogonal. So they fulfill this condition here. And this property is used to construct orthogonal CDMA codes. And now you might have noticed that the length of the code depends on the order of the Hadamard matrix. And this property is used to construct orthogonal codes with different length. And the codes which can be constructed from this are called orthogonal variable spreading factor codes, or in short OVSF codes. And they have a special property. You can implement a variable spreading factor. So the order of the Hadamard matrix actually defines the spreading factor used for the spread spectrum technology. So in the most simple case, the Hadamard matrix of order 1 is used, and it only had one row and one column, so there's only one code. And on the next level, you have a Hadamard matrix of order 2, and you have 2 columns, 2 rows, and you of course have 2 different possible codes. And again, for a matrix of order 4, you have 4 codes, and so on. But the order is always a power of 2, because and for each stage you just double the order of the Hadamard matrix. And here you see that the codes which are generated are arranged in a tree structure. So this is why we call it the code tree. And why do we organize the codes into a tree? It has to do it has something to do with the orthogonality. So you know that, for example, this code and this code is orthogonal. Yeah, they are constructed out of the Hadamard matrix, so they are orthogonal. But now you want to implement a system where different users use spreading codes of different length. So it has something to do that, of course, if you use a spreading factor of 8, you have a lower data rate than if you use a spreading factor of 2. You know that your spreading factor is the ratio between the chip rate and the data rate, and in a CDMA system, so we are here in the synchronous case, so we need to keep the chip rate constant. So what is the parameter which must be changed is the data rate. So spreading factor of 2 gives a higher data rate than spreading factor of 8. So now we want to assign codes with different length to different users, because one user needs a high data rate. It, for example, gets this code here. And a different user gets this code. Now we can do the check here. If we calculate the inner product of the two vectors, then we indeed get a 0. Another example, one user is assigned this code and another user gets this code here. And now let's calculate the inner product, and we see that both codes are not orthogonal. And this has a system. So you see that for the non-orthogonal code, and so for the non-orthogonal codes selected here, you see that the code resides in a subtree of this code. So if you assign this code to one user, all codes below in all the subtrees are not orthogonal. So this code is not orthogonal, and all these codes here are not orthogonal. So you cannot assign the whole subtree to another user. So if you assign one code to a user, then the whole subtree cannot be reused. But let's go back to the green example. One user is assigned this code, so this whole subtree is then occupied by one user. But you have a different another branch here, and this code does not reside in the same subtree like this code, so it can be used for another user, and both codes are orthogonal. This code would also be orthogonal, and if you instead assign this code, it would be orthogonal to this code too, and this code would be orthogonal to this code too. Yeah. So yeah, this is the system behind the orthogonal variable spreading factor code tree. So you use this system to generate orthogonal codes with different length. And now again, let's discuss why we need different length codes. So the central point here is that we have a synchronous Cdma system. So the chip rate must be fixed. So you cannot change the chip rate, and because the both users must be synchronized, and the codes must be aligned. Remember that the code must start at the same time for both users, and to be synchronous, their frequency must be equal, so that their frequency is the chip rate, and yeah, so everything must be aligned. So chip rate must be equal. And now we want to assign different data rates to users. This can have different reasons. One reason is that for a low data rate, you get a better processing gain because you encode one data symbol with more chips. So here in this example, low data rate, you encode one data symbol with 4 chips, whereas in the case for user 2, in the high data rate case, you have only 2 chips for one data symbol. So 4 chips in contrast to 2 chips. And now it becomes clear that you get a better processing gain and therefore improve your signal to noise ratio. And this is one reason why the data rate is dropped, and you can observe this with your cell phone. So if you are in remote places and you are very, very far away from the base station, then your data connection is quite bad. So you have a low data rate. If you want to load a web page, it loads very slowly. Whereas if you are in the city and you are probably nearby a base station, then you have high data rates because you have good signal to noise ratios there. You don't need a high processing gain, so your cell phone can adapt to a higher data rate and pack more data symbols within the same time. So the change of data rate is a consequence of the fixed chip rate. So the chipping rate is kept constant, and now you can select codes of different length, and what is adapted is the data rate in the system. And now you have, in this example, 2 users. One user uses a long code and the other user uses a short code, and so their data rate is different. But you have now codes of different length, but because they are constructed out of the orthogonal variable spreading factor code tree, the 2 chosen codes are orthogonal, and you can use the CDMA here and transmit the 2 signals over the same transmission channel using the same frequency and at the same time. But again, this code only works for synchronous CDMA. If you have an asynchronous CDMA, so the chip rate is not equal for 2 users and the code sequence is not aligned in the time domain, you cannot use the orthogonal variable spreading factor code tree, because then the cross correlation will not work. So you don't get the property which you expected here. So then it will look different. So the green signal would have peaks here, and you won't be able to despread the 2 signals properly. So for the asynchronous case, you need different codes. So the Welch codes out of our OVSF code tree are not suitable. They don't have optimal cross-correlation properties if the signals are not synchronous. So you need to find codes which have better cross-correlation properties in the asynchronous case. And these codes are pseudo-random noise codes. So these codes are quite long, and they really look like noise. And noise means that they have an almost random distribution and equal distribution of zeros and ones. So it's, for example, +1, +1, +1, 0, -1, +1, -1, and so on. So you need now to balance the minus ones. They look like random, so this looks like a random sequence, but it is not random. So the code is, of course, known. It is generated by a mathematical function, and therefore it is called pseudo-random. If you don't know the parameters of the PRN generator, then it is a random code. It's just a random sequence. And but if you know how the code is generated, then you know the code, and then you can use the code to spread the signals of different users. And one example are gold codes, which have good cross-correlation properties for the asynchronous phase. So now you have learned about the codes. You know that you have to distinguish between the asynchronous case and the synchronous case. We have learned the Welch codes and the orthogonal variable spreading factor code tree used for the synchronous case. And here you've learned that you need to have a look at the cross-correlation function of the codes in the asynchronous case to find good codes. But if you are actually interested in the construction of codes, please refer to the literature.